Hi, my name is Mark Hastings, and I'm an application engineer at Cypress Semiconductor. During this video, I will discuss several ways in which you can increase the standard internal 8-bit DACs to as much as 12 bits of resolution. Application note AN64275 provides full details in a library that implements several of these concepts. Natively, the PSoC3 and PSoC5 architectures provide up to 4 8-bit DACs that can operate in either a voltage or current output mode. This unique characteristic allows you to combine multiple digital and/or analog blocks to create a more powerful hybrid component. In this case, DACs with higher resolution. The 4 concepts that are discussed in this video include parallel DACs, 2 current DACs in parallel set to different ranges, dithered output DAC, a single DAC but the output is dithered quickly, a modulated IDAC when we combine a current DAC and a digital PWM, parallel IDACs with ADC feedback, 2 parallel current DACs combined with a delta sigma 16-bit ADC for feedback. There are trade-offs between speed and linearity for each of these concepts. The diagram on the left is a summary of these trade-offs. Resource utilization is an important factor that must be considered. Notice that each of these DACs consume a different amount of internal and external resources. For example, the PI DAC uses 2 VI DAC blocks but does not require external components. If you want to use the PI DAC to source a voltage instead of a current, an external resistor may be added. The modulated DACs, DV DAC and MI DAC, only require 1 VI DAC block, but require external components to filter out the modulation noise. Some applications that require this extra resolution may not require the output to be filtered. Heating and lighting may be types of applications that do not require filtering. The parallel IDAC, or PIDAC as we call it, is implemented by connecting 2 IDAC blocks in parallel. The total current at the I/O pin is simply the sum of the 2 current sources. Note that this concept may be used for a current sink or source. The diagram on the right shows how the 3 IDAC current ranges overlap for a total dynamic range of 14 bits. A word of caution here: just because you have a range of 14 bits does not mean you can achieve a full 14 bits of linearity from a couple of 8-bit DACs. As shown in the previous slide, performance for this configuration is about 10 or 11 bits. The dithered output DAC, or DV DAC, method continuously writes 2 different but consecutive values to the DAC. A simple external filter averages these values to create the desired output. It is somewhat like using a PWM, but instead of dithering the entire power supply range, the output is dithered by a small amount, which is 1/256th of the entire DAC range. By dithering the small amount, the modulation noise is much easier to filter out. Normally, this dithering would require a reasonable amount of CPU cycles, but instead, PSoC3 and 5 have DMA. This can all be done in the background with no CPU overhead, except when the desired output value is changed. The figure on the left shows the schematic of how this type of DAC is realized in a PSoC3 or 5. The table on the right shows a couple examples of dithering the output value. Normally, if the voltage DAC is set to a 1 volt range, each step would be 4 millivolts. That's 1.024 volts divided by 256. In this example, a 4-element dither array is created for a 10-bit DAC. The values of this array are consecutively written out to the voltage DAC over and over. Notice in array 2 that the DMA channel writes 125 to the DAC 3 times and 126 to the DAC once every cycle. Averaging these numbers results in a value equivalent to 125.25, or an extra quarter of a bit of resolution. In this case, it's an additional 1 millivolt. Although the example shown is a voltage DAC, the same concept can work equally well with a current DAC. The modulated IDAC, or MI DAC, is a hybrid between the old PWM DAC and a current DAC. A current DAC is used to set the most significant 8 bits of the current, and a PWM is used to provide an additional 1 to 3 bits by setting the duty cycle of the PWM. The two resistors R1 and R2 can be calculated using the equations on the right. See the application note AN64275 for more information on capacitor selection. The MI DAC is more linear than the PI DAC and is faster than the DV DAC. See table above for more details. If your design needs 12 bits with good INL and DNL performance, but you don't require a fast sample rate, this method may be the right option. This concept is the same as the PI DAC with the parallel current DACs, but you add an external resistor and a delta sigma ADC. The two parallel IDACs are set to the 2 mA and the 32 microamp range to achieve 14 bits of resolution. Since the IDACs are not linear to 14 bits, firmware is used to adjust the two IDACs with feedback from the delta sigma ADC to adjust to the closest fit. Although we have 14 bits of resolution, the 2 extra bits are needed to achieve a proper trim for the 12 bits of linearity. This configuration can give the user 12 bits of linearity, but requires multiple 16 bits readings from the ADC each time the output is changed. This will limit the update rate to about 100 samples per second. These 4 DAC concepts are just some of the ways a user can make good use of the PSOC 3 and 5 analog digital blocks to increase the native 8-bit resolution of the internal DACs. See application note AN64275 for more information. Thanks for taking the time to review this video.